Alright, y'all, let's talk physical properties and chemical changes. So a physical change and a chemical change, this is when we were looking at the Sunset in a Bag Lab, as well as the stations where we bent wires and saw carbon dioxide sublimate, and also did some chemical reactions. So a physical change and a physical change, the molecule at the beginning and the molecule at the end are the same. So if you think about, all right, a physical change, the molecule, the atoms are connected in the same way at the beginning and at the end. If you boil water, it changes phase, but it stays water. The atoms don't rearrange to create hydrogen gas and oxygen gas. It's staying in that same molecule. So a chemical change comes from the bonds between atoms breaking and rearranging to make a new molecule at the end. So, for example, when you take baking soda and vinegar and you mix them together, you make carbon dioxide gas. And that carbon dioxide gas was not there before. The carbon and oxygen that were part of the carbon dioxide gas are coming off of the baking soda and the vinegar. So that is that difference between a physical and a chemical change. Indications that a chemical change is occurring. We have color changes. We have precipitation, formation. So a solid forming in what was the combination of two liquids. We can have an odor change. We can have a temperature change. So endo, exo, right? When we take two room temperature things, we mix them together and we get something really hot or really cold. That's another indication that a chemical change is occurring. And then lastly, evolution of a gas. So formation of a gas, bubbles, but remember, where else when we may see bubbles? We might see bubbles in the phase changes. So phase changes are physical changes because if you make something melt, it is still the same molecule. It is just changing how fast it's moving. It's literally just how much it's bouncing around, right? So if you melt a material or a molecule, a bunch of molecules, they stay the same. There we go. It's just changing how fast it moves. Cool. So phase changes are physical changes. Remember that includes melting and freezing, so that difference going between liquid and solid, evaporation and condensation, which is liquid to gas and back, or sublimation and deposition, which is going between solid and gas without passing through liquid. Great. These are all properties that do not change with amount, therefore they are intensive. So intensive properties do not change with amount. We can use them to help identify something. Mass, volume, and shape are all properties that do change with amount, therefore they are extensive properties. So extensive properties here, intensive properties here. Again, intensive properties like boiling point and density, where the amount has been factored in, they don't change with amount because in the calculation we're dividing by amount, and it makes it consistent and predictable for density. So let's talk density. Density is how tightly packed atoms or molecules are in a particular volume. That's the non-technical definition. The technical definition is mass per unit volume. And this is our equation. Density equals, density is mass per unit volume. We've got our broken heart equation, density equals mass divided by volume. If you put the m over the v, it kind of looks like you cut a heart in half. So we calculate density by taking mass, dividing it by volume, and that contributes to where our units are coming from. because it's going to be grams per milliliter, or some mass measurement over some volume measurement. Great, calculating this, we're going to have 4.0 grams, a volume of 2.0 grams. So let's go over onto the paper and check this out real quick. All right, so we know that density is mass divided by volume. If we look at our problem, it tells us that we have a mass of 4 grams and a volume of 2 milliliters. Always fun to find those typos. So 2 milliliters. So 4 grams and 2 milliliters. We're just putting it into the equation, right? Our mass is equal to 4.0 grams. Our volume is equal to 2.0 milliliters. The density of our object is going to be 4.0 grams divided by 2.0 milliliters. That's going to give us 2.0 grams per milliliter, which means that for every 1 milliliter of space, we're going to have 2 grams of mass for this particular material. Let's check out the next one. So we have a piece of gold with a mass of 8 grams. How much space will it occupy? Okay, so in this case, we are using the same equation. And remember, there are options here. You can either memorize one equation and kind of know how to manipulate it. I'm going to write down 8 grams, and then also 19 grams per milliliter is the density of gold about. So we can either memorize just this one equation and have the algebra chops to manipulate it. So I'm going to do that first. So first example of solving this, I'm going to put 19 grams per milliliter because that's the density of gold about. On the left side, that's density. I've got 8 grams for mass, and I have volume as an unknown. So just like in algebra class, you can multiply by V. I'm going to have 19V is equal to 8. V is equal to 8 divided by 19, which is going to get us just a little bit over 1/2. But I'm going to go ahead and write 8/19. And the really cool thing here is that we have grams, and we've got grams per milliliter. And so what happens mathematically is we end up multiplying by the reciprocal. The grams cancel out, and the only unit we're left with is milliliters. So that math manipulation with units becomes more and more fun as we go on in science classes. But all right, that's our first way of solving this. The other option you have is to write down or memorize your 3 manipulated versions of this equation, where you just use the correct one for what you're given, right? So if you write all 3 of these down, these 2 are just manipulated versions of this. So they are all still true, where we are just having the unknown set up already for us. So in this case, volume, well, that's the unknown. That's what I'm looking for. I want to see what volume of gold I've got. And so I would take just the mass, which was 8 grams, divide it by the density, which was 19 grams per milliliter. Again, these grams would cancel out because we're multiplying by the reciprocal, and this would be equal to 8/19 of a milliliter. All right, so those are your options when solving these problems where you have to manipulate the equation. All right, this last version you may be able to guess. The first one we calculated density, the second one we calculated volume. This one we're going to be calculating the mass, right? How much mass will a piece of neoprene rubber that occupies 3,000 centimeters of space, and we have that density as well. So coming back over, I'm going to go ahead and write down my numbers. I've got a density of 1.23 grams per centimeter cubed. I've got a volume of 3,000 centimeters cubed. And let's go ahead and look at solving this. So Again, you can do this by putting it into your equation and solving for the unknown, but I'll do another example of using these three for folks that are wanting that support. So if we think about it, all right, this is density, right, because we measure it in grams per centimeter cubed. This is volume because we measure volume in centimeters cubed, a distance cubed, or a graduated cylinder liters or milliliters measurement. So my unknown is mass. If you look at the three options we have of the manipulated expression, mass is density times volume. Well, density is 1.23, volume is 3,000. And just because I love it so much, we can also see these units, okay? Centimeters cubed times centimeters, just like in dimensional analysis, those cancel out and we're getting to this unit of grams. So when we do this, let me check real quick. Great, so doing that calculation, 3,690 grams of neoprene rubber would take up 3,000 centimeters cubed of space because the density is 1.23. Great, so the last thing that we want to be able to do is related to the two labs we did on density, where we used a graph of mass versus volume, and we did a density column. And so with mass versus volume, we calculate the density of the unknown material by calculating the slope, because in that graph, you've got the y-axis as mass and the x-axis as volume, mass in grams and volume in milliliters. And so you're going to end up with a line that looks something like this. Obviously, this is a sketch. Most of the data points should be fairly close to this line. And when you calculate the slope by picking a point here, and then doing y2 minus y1 over x2 minus x1, as we've done in that lab, and then two other instances of calculating slope, this number that you're going to get, well, it's measured in grams per milliliter. And a best fit line, function of the best fit line in this case, is it's averaging the relationship between mass and volume. And if I just picked two of these points, I would get the density, the slope between those points, and maybe I could get it between those points. But by having more points, we're going to get kind of a truer relationship as long as they are all fairly tightly related to the line. And when we calculate the slope, well, we're calculating this difference in grams per milliliter, and we know that this is density, right? So the graph is allowing us to calculate the average density for several measurements. For the density column for number 2 here, remember that things that are more dense, so have a larger density, like 4 grams in this grams per milliliter in this example, those are going to be denser and they're going to sink to the bottom because that mass, that amount of matter is packed more tightly per unit volume. That's what I've got here for physical and chemical changes, y'all, as well as density. Cheers.